Good morning, good afternoon, and good evening for those of you who have logged into this webinar on augmented vision systems. I'd like to welcome all of you who've actually logged in so far. I know people are still joining at the moment, but we're going to actually start this presentation. So I'd like to warmly welcome you to this second part of augmented vision systems, the what, why, and how of integrating advanced vision applications. Before we get started, I'm just going to go through a little bit of details on this webinar. We're aiming for this session to last around 1 hour. However, we will be available to stay longer if people have questions and want to kind of find out more. We will be able to address these questions at the end. There is a chat button in the WebEx view, which we encourage you to use. Please use this chat window to enter questions. What we'll try and do is actually answer as many of those at the end. We'll try and collect those together and go through with answering those at the end of the session. We'd also appreciate that when you leave, there will be a little survey that will pop up in your web browser, and we'd appreciate if you, when you leave the meeting, just kind of fill it in. Just give us some feedback. This is the second one of these webinars we've done together with Clkhr and Presagius, and obviously we're looking at how we can improve and kind of content that's useful in the future. So if you could do that, it's much appreciated. So today, what we're going to do is very quickly look at augmented vision systems, the what, the HMI side, and the how of putting this together as well. So this kind of a very brief view of what it is. The kind of true agenda is we're going to introduce who's talking to you, and then we're going to break it down into two parts. We're going to look at the augmented vision systems, just introduce the types, some of the HMI design considerations and challenges that we have here, and look at the latency problems as well with some of these augmented vision systems. In the second part, we're going to look at some of the system technology, algorithms, how they can be applied, the standards and safety around that, and then we'll kind of end up with a conclusion and question period on all of this. So I'd like to actually introduce who your presenters are today. I'm talking to you here from the UK. My name's Matt Jackson. I'm actually the technical product manager at Presagius for our HMI software. I have a background in embedded hardware and software development, working in this area for over 20 years, and been specializing in HMI systems and real-time graphics. What I'd like to do is introduce my colleague Lucas from Clkhr.
Hey, thank you very much, Matt. My name is Clkhr Gl. I'm a field application engineer with Clkhr. I've been working with Clkhr for over 5 years, specializing in developing graphics and compute drivers for modern GPUs for safety critical applications. I'll hand it back to you now, Matt.
Thank you very much, Lucas. So just as a background, this is the actual second part of a two-part series on augmented vision. So for those of you who attended the previous webinar, I apologize, this next bit is just a kind of a quick grounder on the kind of terminology and parts of the kind of phrasing and the actual types of augmented vision systems that are available for you. If you haven't seen the first part of this webinar series, please feel free. It's actually available on YouTube to go and view, and you can go in and actually watch that again, or watch it for the first time if you want. But for those of you who did see the first one, I apologize. I'm going to be repeating a few of the details, but much more quickly in this part here, just introducing augmented vision systems. So what I want to do is just kind of get some of the terminology and understanding of where we use this and why do we use augmented vision systems here. So just to start with, I'm going to break it down into kind of the key areas. So I'm looking here at the beginning is we've got augmented reality, and there's actually two types of augmented reality. In this case, I'm actually showing here, there's augmented reality, which is two-dimensional. It's the sort of thing that we're used to seeing on a head-up display or a head-down display, or even in a helmet visor. So in this particular example, set of glasses, where we're actually seeing data presented, so many text messages, time of day. It's in your line of sight, it's in your vision. Head-up display, we've got the telemetry overlaid, and that could come in with a piece of glass or a visor or so forth. But the idea is we're presenting all of this in front of your line of vision. The second kind of type of augmented reality is actually the newer type that people are more looking at now, and that's actually an augmented reality in 3D, often referred to kind of as mixed reality. Effectively, what this is actually a computer generation of symbology or people or objects, and it's positioned in 3D space. So what this means is content is added to the real world as if it was really there, hence the word mixed reality. So you have computer generated graphics that become part of the world around you. Why do we want this? What's the benefit for this? What it does is add to reality. So it gives us the ability to show things like flight paths, and instead of a 2D representation, show it with 3D kind of height, position, all of that in front of us in a 3D space. It can also show things like threat zones, or we can actually look at landing corridors. So in this particular example, we need to land somewhere on that island. We can actually project a corridor in 3D space into the scene and actually give you the kind of path that you need to follow. So rather than just looking at waypoints, we can actually fly through the tunnel and do that. So as we move along, the path changes and you can actually see your corridor changing. And this is an augmented reality environment. And the difference between the 2D and the 3D is, in fact, in the 3D, we have the concept of depth. So we actually have to integrate with the world around us and know how far away things are. So moving on from the augmented reality, there's the virtual reality, kind of VR. And effectively, this is a computer regeneration of the world around us using data. So in this particular picture here, I've got an aircraft. It's not real. It's actually a 3D model that's been reconstructed by a bunch of polygons and textured with a skin and positioned in space as if it was the real thing. So we've reconstructed the real world here and we're flying it in a virtual terrain. And this is a 3D rendering of the world around us based on a set of 3D data points, either from a database that's stored locally or from kind of live telemetry that we reconstruct the world around us. So maybe a LiDAR scan where we create a point cloud and then a nav mesh vector mesh of the world, which we then texture or just do solid. And sometimes this is referred to kind of as a synthetic vision on there. So the idea being is we can reconstruct and give a presentation of the world around us without actually seeing that world. So the computer regenerates everything around us and we're not actually seeing the real scene. Now, quite often, and we're going to look at this, is you'll find that virtual reality and augmented reality will get blurred and mixed together. So there will be parts that will be blended together in all of these systems. And so just moving on from the virtual reality, looking at computer vision, and this is kind of the key part that kind of joins this all up together and that kind of makes things possible today, is this concept of the computer being able to see things as if it was a human seeing things in the scene, but extracting information, processing it faster than a human. If it's kind of sensors or just visuals, if it's sensors, it could be doing processing to extract data. So the idea is from this scene, it's tracking objects on the ground based on a camera, and it's turning that into data that we can actually either show to the pilot or the user of the display system, or can be used for making decisions of what we display or what we do within a flight deck or inside a control system. So I just wanted to introduce those topics before we actually look at some of the things around the augmented reality development tasks and what are the challenges and the things we have to consider when we're actually building this as an HMI. So I'm going to dive on in here and look at what typically all this means when we're building an HMI and wanting to build one of these augmented vision systems. So kind of stepping back to the augmented reality in 2D, which is what many people have been familiar with, just never used this terms. Effectively, most of the time, this can be considered as what is known as a painter algorithm. So the last thing that we painted on the screen is shown on the top. So for the head down display, that's fairly straightforward. If we're looking at a computer screen and it's got a camera view and we're showing it on that computer screen, we draw symbology on top of that. And it's the last thing, it's just masking out whatever's behind. For the head up display, quite often this is just projected in front of the pilot's eye, either via a piece of glass or kind of an eyepiece or something like that. But effectively, it's the same concept. We're overlaying and forcing it on top. And all parts of the scene can be considered a flat layer without depth. So if we were looking at this, contextual data in the augmented layer works in kind of two-dimensional coordinates. So for this particular scene, if I wanted to put symbology over the helicopters in this scene, I actually just have to work out an XY coordinate to plot the center of my circle. And often that's kind of not a huge computational task because actually it's a simple vector calculation, either as a range bearing that we can turn into a simple maths on there, because we only actually have to put this in an XY position. So we actually overlay the symbol. And we actually don't need to know about the depth of how far away those objects are. We just need to know the kind of angle away from our center point and work out an XY to plot on here. So obviously that's kind of in the head-up display. Actually, in the augmented reality type of approach, when we're layering up things, and you'll see why I'm talking about this shortly, is I can actually look at how mapping systems work today in a cockpit. And often it works in a similar way that we have effectively a map projection, and traditionally it uses the same concept as it's a layered approach. And we project layers and we stack them up. So we have an XY projection and then layer on top of those the data. So in this particular case, I've got a layer which actually in this case has actually got some elevation information in there, but I'll then be putting chart data on top of it, and then I'll be overlaying my symbols on top of all of this and just positioning them geo-referencing in an XY plane on top. Now, often we'll actually then do and use some of that elevation data to do line of sight. And people will be familiar with this when you're looking at digital maps in a thing. But often when we're using this in a two-dimensional, we use a sampled set of points based on the resolution of our terrain. So in this particular case, obviously I can just show here, we can see the symbols are layered on top of the map, and underneath it is some elevation data, and we have the chart on top. But if I wanted to do a line of sight, I wouldn't actually calculate every single point because there's no need, because actually, one, the resolution of my data is not good enough, but two, it doesn't actually show me anything relevant in my two-dimensional scene. So in this particular case, I can do a set of scans and do a line of sight and give myself a kind of view of, well, how far can I see from this direction from one object to another? And I will then just fill in those points as a set of polygon, as a polygon. And it doesn't matter that I don't have an accurate infill between those sampled points, because in this particular scene, it's not particularly relevant and it's not required. So you can see that, yes, there's a more data being processed, but we don't have to process huge volumes. It gets interesting when we start moving into the augmented reality of 3D though. So this introduces kind of this augmented reality in 3D, we have a depth issue. So if we were to use a painter's algorithm, so in this particular case, if I took my out the window view, either as a camera sensor or I just looked out of my window and I just drew a 3D object in front of it, so in the line of sight of the user, you would see the kind of image that's projected in front of you at the front of the screen here would get a red box presented on there. Now, at first glance, you go, oh, brilliant, I've got my 3D object, it's painted on the scene, it's great. The problem with the painter algorithm is there's no concept of depth. So actually you end up with misleading information. Now, at high altitude and kind of angles looking down, if we're flying an aircraft from very high up, you basically don't notice this because actually you're looking at it almost like the 2D map representation. You're effectively a top-down view. You don't need to worry about the depth because you're so high up, there is no such thing. There's nothing blocking your view. So in this particular case, I've got a set of waypoints. I'm going to be flying over a top of a mountain by the looks of it, and this is what's going to happen. So from this angle, it's fine. It doesn't mean anything, but it's no more information being presented to me than I would in a 2D map. However, if I come into a more shallow angle, if I move into a lower altitude and I look at this situation again, if I use a painter's algorithm, I can see the same waypoints, but I'm starting to see possibly a perspective issue here. Now, it could be that my final waypoint is actually in front of the mountain. In this particular case, though, that's not the case. My actual waypoint, if we looked at our top-down view, was actually behind the mountain. So in reality, I would need to plot something like this. And that actually requires you to be able to clip your graphics based on some depth data and do a correlation of that. Now, there's many ways of approaching this problem, but it becomes very important because the previous scene was misleading. It showed you a set of waypoints, but in fact, those waypoints were either the pilot input them incorrectly, or they need adjusting, or there's been an error in correlation. Reality is those waypoints, if I tried to fly them, I would have a problem because actually the altitude between them would mean hitting the side of the mountain. So this is a very kind of obvious case, but it's been designed on purpose to show this problem. So how do we actually overcome that when we're looking at this sort of depth? Now, we've talked kind of about this. With the 2D maps, we have data that's actually a data set. We can have DTED information where we can do line of sight calculations, and you can actually use that just to present in a 2D map. So the same can be applied in a short range system, but actually we have other things we can use to actually help us get some form of correlation to the world around us. So in the short range, use of cameras, LiDAR, and offline databases can actually help us in this particular case solve the problem. If I'm looking further away, you'll notice that I've kind of removed the camera because actually cameras at a further distance, we get some problems. They're not impossible to overcome, but typically it's a different type of issue. We still have the same thing. We can use radar, we can use laser, kind of LiDAR, we can use database, and we can also use telemetry. And actually you can use all of these in the short range as well. It's just whether or not it makes sense. I kind of mentioned the word telemetry because actually if we're looking at airfields or we're looking at landing platforms, we could actually have radio beacons that are giving us accurate data about height, position, and sending that back live, telling us a more accurate information about where we're going. So these are all things to be considered when we're actually trying to plot and do some form of correlation for this augmented reality in 3D. So the question then comes is, okay, that's great. We're now doing some form of depth. What we've got to be aware of is actually this generates a lot more information, and how do we present that, and what's the right thing to present? So I've got a little worked example here. here. So I've actually got a kind of 3D mock-up here that's of some terrain and some mountains again, but done as a 3D model. And if I look from a top-down view here, I've actually got a symbol and it's actually hidden behind the mountains. So because I've got no depth clipping, I see it. It's actually here and it's shown. Now, if I actually come in and consider this case, flying at a medium altitude, I'm looking down at a 45-degree angle. So this is actually measured at a 45-degree angle. I can see that symbol because I'm actually high enough above to actually see it. I'm looking at an angle at such a way that that actually object is being shown. Now the symbol is actually being partially shown. And the question arises when you're doing an HMI presentation is, do I actually want my object, my 3D object in space, partially occluded, fully occluded, or some other thing here? Now, if I'm going for this approach, if I wanted to actually show this symbol as partially occluded by the mountains, if I refer back to my kind of 2D map approach where I did line of sight calculations, actually I have to sample the whole edge of my mountain. And I actually have to sample the mountain in front, and I have to get the whole shape of everything that could be possibly occluding my symbol. So actually there's a lot of data points that I would actually have to generate to work out what occludes that object shape. And the question actually comes to you from the human factors point of view, is this clear anyway? In this particular case, most people would say, yes, it's clear. However, as I'm coming in to a runway approach or something like that, I have a symbol, and you can notice here, this is a shallow view angle. This is actually a 10-degree angle coming in here. I'm a kind of a fairly low altitude. You'll actually notice that I can't actually see that symbol at all almost. There's a little green peeking out from behind the mountains, and it's hidden. So there are approaches you can consider in terms of an HMI, because this is typically you're drawing these things because it's useful information for the pilot or the user. So one of the approaches people take is actually saying, let's put a drop line to indicate that that symbol is hidden. So here's the same thing here again, but what we do is actually put a secondary symbol and connect it with a new 3D object, indicating that this is an obscured symbol and it's down here somewhere. So the idea of a kind of a drop line to actually indicate where that symbol is so that the actual user gets relevant information is one approach. There are other approaches. You could actually say, let's move that symbol and project it in front of the scene, change its appearance, color, markings, or something like that. The kind of thing to take away from this is you've got to consider what's useful, not a distraction, and relevant for the actual task that's going on in place. So this is the same one here again, but actually a view angle of 35, and we're a fairly close position, and it's partly occluded again here. And here's a drop line just indicating what it really looks like in 3D. And the thing is, what I'm trying to get across here is presenting this data is not the same as we're used to doing head-up displays or just kind of presenting it in a 2D plane. We've actually got to think about how we present this differently. We also have to think about how we collect that data and work out how it's occluded and what the rendering scene needs to be. So, having obviously talked about some of the HMI and the things we have to look at when we're building, I want to just move on to kind of the other issue on the HMI side with this advanced vision systems here, and that's latency. So I'm going to look at this purely from the HMI point of view and what the consequences are. Later on, what we'll do is talk, Lucas will be talking a little bit more about how we can improve the performance by using some of the technologies that are available. But what I'm going to do is just introduce the kind of problems we have to think about. So as a user, effectively, the challenge we have, it's the latency to the screen. And actually, it's made up of many things of why does it take so much time and what's going on before we can actually get a picture to that eyeball. So in this case, a screen render or something like that. And I've simplified it slightly here, but effectively we've got multiple things that are accumulating here to build up the timeline that's going on. So the first thing that we're thinking about is actually the position tracking. So this is important because actually there's a lot more than just simple position tracking. But if we look at position tracking, we can simplify it and say, hey, we've got the aircraft, we're moving around, we've got a latitude, longitude, altitude, heading, pitch, roll. You're generating that all the time. So you're always got that information from your platform. It gets added complexity on there and an a faster rate of data change if you actually introduce the concept of a helmet or a sensor that's moving. So in some cases you may have a camera on a gimbal and that's got a movement and that's located on the platform. So you're adding the vehicle movement to the position movement of either a person's head or eye line or a sensor movement that you're using to feed a screen. So that's kind of generating a constant update that you have to take into consideration when you're plotting the data on the screen. We then have data processing. So it's taking the positional information that we're getting in, but it's actually having to take all of either if we're using a database or sensors to do depth positioning, or other systems to actually work out what's relevant. And the idea is we then have to correlate that as well. So we're trying to correlate all of this information. And eventually, once you've done all that heavy kind of computer processing, you have to get that pixel to the screen. And what you need to do is kind of minimize that pipeline. Otherwise, you end up with some interesting effects that cause problems as you go through. Oh, the wrong way. So we can see this, the effects of latency, and we can think of it in the simple case. If we're used to the traditional 2D approach, a head-up display, if I roll my aircraft and my head-up display doesn't move, it's a bit annoying because actually the head-up display catches up eventually, it kind of moves and you see it change. So at worst, it's kind of annoying as a distraction. It's not good. Kind of at best, I mean, at worst, it gives you incorrect information. Now, this is the sort of thing that actually over the years, most of these systems like this don't have this problem because we know it's an issue. If we look at a 3D approach, where we're doing an augmented reality, if I've got a kind of flight points here and I'm representing them as pillars on the terrain here, you'll notice in this particular example, the problem with latency is actually different, but similar at the same time. The problem is if my aircraft moves and I kind of roll to the left and I don't update my graphics quick enough, you end up with all your items floating in space at completely the wrong location. So the problem with that is they're sitting there at the wrong location, giving you the incorrect information. Now, this gets interesting because actually from a distance, and this is where it comes down to aircraft velocity and movement and position tracking, if we're at a very high altitude, looking from a long way away, actually a movement in this particular case, I've lost correlation by approximately kind of 100, 200 meters. It doesn't really matter. You wouldn't notice it from a long distance. But if this is my approach coming into a runway or a situation where I need to avoid things, that becomes a problem. You get this issue, and then there's a case of, well, how long does it take before the next symbology update rate catches up? And then you find that it jumps. So it's now resynced here into the correct location and jumped back and resynced. But if you see this situation going on, what you'll find is your symbols jumping. So as you're moving around a scene, your actual symbology is jumping around. It's not actually keeping up with what's going on around, causing you a distraction and misinformation. The other problem, obviously, with that is there is this concept of if you can't process the information and present it at the right time, you can come up with the scenario where effectively your symbology pops up, but very, very late when it's no longer relevant. So as I'm panning around, all of a sudden I pop up the symbology and it was a marker on the left-hand side. I'm almost past it. So it took too much time for that information to come up. And at this point, it's almost irrelevant because it's almost out of my visual scene. So that data was too late. This is the kind of challenge we have when we're trying to do this, and we're trying to minimize all of this. So getting this graphics to the screen and that throughput. So what I'm going to do is hand over to Lucas, who's going to talk about some of the approaches and the algorithms of how we kind of do the depth analysis and how we manage the look at the scene, but also how we can improve that data processing to the screen pixel. So over to you, Lucas.
Okay, thank you very much, Matt. So I'm going to take over from here. In my portion of the presentation, I'm going to talk about, like Matt said, how we do some of the processing. Like if we're trying to gather depth information about the scene, how can we do that from the sensors we're getting, and how can we do it in an efficient way that leads to low latency? Then I want to talk about some standards that exist right now to ease the development of high volume compute applications that you would use for augmented vision systems and advanced vision systems. And lastly, I want to talk about the safety of all this. So first, just a little rehash, a little bit of what I talked about in part one of this webinar. If you attended part one of this webinar, I apologize. This will be just kind of an overview of my portion of that presentation a couple weeks ago. But when we're doing advanced augmented vision systems, an important part is gathering data from sensors. And when we're talking about three-dimensional data that has depth information for a scene, it's large data sets, and then comparing those data sets from multiple sources, processing them, and then displaying them or visualizing them. And when we need to do this in real time, so for example, if you have a display, you might be updating it somewhere between 30 hertz and 60 hertz, or if you even have a heads-up display, the refresh rate becomes more and more important. You could be updating at a rate faster than that. If you're using, for example, a radar or LiDAR sensor that's gathering a point cloud of data, that per sample, you're looking at hundreds of megabytes to even gigabytes of data. And if you need to update that at 60 hertz, for example, you're looking at, 30 gigabytes per second or even 60 gigabytes per second of data that you now need to process in order to display something in real time. Now to talk more about this visualization process and how we can make sense of the data that we're getting from sensors, I'm going to use the example of a terrain overlay system where we're getting data from, for example, a database that has a point cloud or LiDAR sensors or radar, and it's providing the system with a point cloud of data that has positions of where objects in the scene sampled at, points that have a certain resolution. And if you're looking at my picture here, you might think, oh, this is a pretty common application. I've seen it in the world today. Aircraft are using it right now, and that is true. This type of system does exist in aircraft today, but typically systems like this rely on offline process data. So they will have a map database and typically a point cloud database that has been pre-generated days, weeks before, maybe, where another aircraft has flown over the scene, captured the data, brought it back to base. It's now being processed either, using a supercomputer or a high volume compute system of some kind, and then this pre-processed data is being uploaded to the aircraft that's going to fly later. And so this is not live terrain data. So if there's any kind of changes, so if there's any construction that's gone on, if there's been any weather events like landslides or hurricanes or storms, and that has modified our terrain in any way, the data is no longer live. So we can't trust it for doing really accurate mapping in real time. And so to improve this use case, I want to look at using real-time processing of sensors and correlation of sensors to actually have a live update of this type of terrain data. Now, why would we want to process the data? Well, if you look on the right here, there's an example of point unprocessed point cloud data, and it's very noisy when you look at it. There's lots of points. It's difficult to tell what the points are representing. Are they a building? Are they the terrain? Is it something that I need to be concerned about? And they have spaces in between them. It's difficult to determine the actual volume of the shape that they're representing. And as a pilot, it's distracting to put this cognitive burden on the pilot to process these points in their own head and try to reconstruct mentally what these are representing. Also, from a computer vision perspective, it's difficult to make determinations just at the point cloud level. So something that we want to do is reconstruct the surfaces that these points represent. And the algorithms that I'm going to be talking about right now are going to be focused on this problem, reconstructing the surfaces that a point cloud represents. And to do it in real time, we're going to need high volume compute since these data sets can be quite large. So the class of algorithms I'm going to talk about right now fall into a general category referred to as isosurface extraction. And it's the process of creating a surface from volumetric data like a point cloud. And it's used in many domains, so it's not just for terrain data. Medical imaging is another big place where isosurface extraction is used. But in our case, we're going to use it for creating a terrain surface from point cloud data. And so the idea here with isosurface extraction, we have these points, they represent some surface. And so we're gonna try to determine where that surface is in the points, and then finally get, some mapping of the terrain as three-dimensional polygon data that we can use either for visualization or correlation with different data sets that we're getting from different sensors. So it can act as a kind of normalization of our data that we're getting from different sensors so that we can compare the results from the sensors and correlate it with, for example, a pre-calculated database. Now, the specific algorithm I'm going to look at here is marching cubes. You might have heard of it before. It's a very popular and efficient algorithm for isosurface extraction. It's used frequently since it's simpler to implement. It works very well in the average case, and there's variants of it that exist that are accelerated very well either on multi-core CPUs or in our case, what I really want to focus on, GPUs. And so how does this marching cubes algorithm work? So when we have a point cloud of data, there's just, a bunch of points in space with some position associated with them. And marching cubes gets its name from looking at a single cube of that data set and then checking whether the corners of that cube are inside or outside the data set. So how close are they to the points that we're actually looking at right now. So we check each of the corners. If they're near points, then we know that they're inside the surface. If they're not, then we know that they're outside the surface. And the algorithm is going to look at which of these corners we can determine as inside and outside, and then use that to with a lookup table to determine what polygon best fits this cube for making the surface. The other thing that it's going to do is linearly interpolate the polygon based on these points. So for example, if the points that are inside are very deep inside the polygon, we're able to determine that they're far away from the actual points themselves and deep inside the polygon, then we can push the polygon we're using to represent the surface towards the outside of the cube. And if these points are very close to the surface, then we're going to want the polygon that we use to be very close to these points in the corner. So in this specific example, we're going to say that it's about halfway in, so it's somewhat far in. And if we come up with a polygon for that, it's going to look like this. So the points are fairly close to, the polygon is fairly close to the points that were actually inside the cube. The idea here with marching cubes is that we're going to repeat this process for all cubes that represent the grid of our volumetric data. And the way the lookup table works is with these specific polygon shapes is that they can all connect together. So all of the pre-calculated polygons that we use in the lookup table are specifically chosen so that they connect to every other polygon that we could possibly use. And so this is a fairly standard, easy way that we can build up a surface for the point cloud data that we're using. And this algorithm was actually published in a patent by two researchers from GE. William E. Lawrenson and Harvey E. Klein. If you're wondering about the algorithm, the patent expired, I believe, in 2005 or 2006. So it's been in the public domain for a long time now, and that also leads to why it's been so widely used. It's a well-known algorithm that people are allowed to use without having to worry about any kind of patent infringement. And it continues to be used as a standard algorithm simply because it's fast, and it can also be accelerated by devices like the GPU. And that's what I want to focus on next. How can we accelerate this using something like a GPU that's capable of high volume compute, so that if we have a point cloud that's represented by gigabytes of data, we're actually able to do that in real time. And if you look at research, academic papers, that kind of things, you can find lots of examples of accelerating the Marching Cubes algorithm. There's examples of using fragment and vertex shaders on GPUs, examples of using geometry shaders on GPUs. And there's also examples of using compute shaders on GPUs. Now, I'm going to focus on the last one here, the acceleration using compute shaders. And the reason I'm going to focus on this is because it allows us to use the data for more than just visualization. If you look at when those older papers were published, they were published before compute shaders were generally available on GPUs. So things like CUDA, OpenCL, Vulkan, those didn't exist back then. And if you're familiar with the timeline of using GPUs for more general purpose computation, you'll know that first things that were exposed programmably on the GPU were the vertex and fragment shaders. And so when those were exposed back in the early 2000s, researchers began to try to use them for more general purpose compute operations, where they tried to reframe their problem as a vertex processing problem or a fragment processing problem. And then geometry shaders came out shortly after that. And again, researchers tried to refocus how their problems on a geometry processing problem. So when we're using vertex shaders or fragment shaders or an algorithm designed around that, it's kind of a, I'll say, quote unquote, hack to fit the processing into GPU compute. But since the mid to late 2010s, general purpose GPU compute has been a technology available on GPUs that allows us to not have to reframe our problem as a geometry processing problem, a vertex processing problem, or a fragment processing problem. We can actually write a general purpose compute algorithm that is not tied to the actual visualization of the data. We can store the data in a buffer that we can access by other parts of our application to do things like correlation from different sensors. And so that's why I want to focus on the compute shader part of this, because for us, when we're talking about HMIs, the visualization is important, but when we're talking about safety, it's also important to correlate data from different sources so that we can ensure that there's redundancy in our system. Now, how does this GPU compute shader accelerated version work? So in the previous slides, I had a link to a research paper published by D'Agostino and Sienstra that provided an example of accelerating marching cubes using NVIDIA's CUDA APIs. And the ideas these researchers took here and the reasons that they used NVIDIA CUDA was, at the time when they published this, I believe the paper was published in 2015. CUDA was really the only viable approach to do general purpose GPU compute. I believe OpenCL was out at the time too, but CUDA is where all the serious people doing research were doing their work. And the idea they took to accelerate this on a GPU was to partition the point cloud data into chunks. And you might think that the marching cube is already processing the point cloud data into chunks. It takes a cube and then it compares the 8 corners of the cube. But the idea they took here is to partition it larger than that, so you'll have a chunk made of many different cubes. And then you'll assign these chunks to work groups on the GPU and implement a standard marching cubes algorithm in the compute shader that takes advantage of the vector processing operations that are available on the GPU to accelerate it slightly, and then do this partitioned parallel computation where each work group on the GPU is working on building up the surface for that entire partition chunk. Now, the interesting thing about this approach is that it's actually extendable across multiple GPUs. When we're talking about real-time safety critical applications, this isn't super useful to us because then we start having to worry about copying data across multiple GPUs, and it introduces the problem of latency associated with data copying. In the first half of this presentation, or sorry, in part one of this presentation, I talked a lot about the latency associated with copying data. So this isn't really useful to us, but ignoring the multi-GPU functionalities that were discovered with this algorithm, it allowed a performance increase of 45 times over just using the CPU. And so this was back in 2015 when GPU compute was just being brought out, and the knowledge capabilities and the power of GPUs isn't anywhere near what it is today. And so from this alone, you can already see that there's a substantial performance increase from moving to GPUs that would allow us to do a lot of this type of work in parallel and in real time. Now, you might be thinking, oh, this is really cool. We can process all this data. This is amazing. But at the end of the day, why is this important to us? And I really don't want to focus on just the point cloud algorithm here or extracting surfaces from point clouds. There's more to what GPU compute is providing to us than just doing point cloud computations. And modern aircraft today have GPUs that are more powerful than ever before. And this is for a number of reasons. So there's a need to drive higher resolution display panels, for example. We're always hearing requirements for 4K or even 8K displays. And when you start having the need to drive resolutions that are that high, you need to use more modern GPUs that are more capable for general purpose compute. And these new GPUs that are coming out that can support these, high resolution display panels are being designed, at least in the commercial space, to be used to solve more problems than just graphics. So when you look at the latest GPUs from AMD, from Intel, from ARM, these are all GPUs that are trying to expose general purpose compute capabilities for other applications like high volume compute, like artificial intelligence, like neural networks. And so these modern requirements that have nothing to do with high volume compute are putting hardware that is capable of high volume compute in modern aircraft. So this is kind of enabling something that we haven't seen before. There's new hardware being put in aircraft that is more capable than it ever was before. And modern standards are being developed today to expose that in a more portable way to allow the development of general purpose compute applications. And so if we want to take advantage of all the hardware that we're putting in aircraft today and use it to its strengths, for example, showing the point cloud application here, the GPU can work much more efficiently at processing these parallel data sets than a CPU can. And so if we want to take advantage of this hardware, we can use these modern standards and this modern hardware to enable applications that we weren't able to see on aircraft in the past. So this leads me into my next point, modern GPU standards, or general purpose GPU compute standards. And the first couple slides here is going to be a bit of a rehash of part one. So I'll go over it quickly. I apologize if you attended part one of this presentation. But in part one, I briefly covered two standards. There's the Vulkan Safety Critical Standard and the Openvx standard, specifically the feature set in Openvx called the Safety Critical Deployment Feature Set. And so both of these standards are developed and maintained by the Khronos organization. If you're not familiar with Khronos, they're the standards body responsible for the OpenGL, OpenCL standards. And they also have working groups within the organization that are focused on doing safety critical variants of these standards for example, the avionics market. Now, Vulkan Safety Critical, or Vulkan SC, is the next generation graphics and compute standard from Khronos. So it's focused on providing a safety critical subset of the Vulkan standard that can be used in, for example, avionics applications. And it's focused on exposing modern functionality available in GPUs. So this is stuff like compute shaders for general purpose compute and more advanced graphic features like geometry shaders and tessellation shaders. And for us, when we're talking about advanced vision systems with advanced augmented vision, one very useful case for us is that it allows the GPU to be utilized simultaneously for both graphics and compute operations. And so what does this mean? Well, in order to understand that a little bit better, I want to compare what Vulkan SC is doing to OpenCL and CUDA. And so these are OpenCL and CUDA are two very popular GPU compute libraries. and they both do not have native support for graphics. So for example, in OpenCL, if you want to share resources between an OpenGL application for visualization, which when you're talking about HMI, that's very important. You're doing all this high volume compute. You want to visualize it for the human machine interface. There's an extension in OpenCL called Clkhr Gl Sharing that allows you to share data between OpenCL and OpenGL. And this comes with a lot of caveats because now you need to have careful state management between what API is currently owning that resource. Is it being owned by the OpenGL portion? Is it being owned by the OpenCL portion? And you have to do this safe passing of the data between the two. Now, CUDA also has a similar approach for sharing. It has its own extensions that allow the sharing of data between OpenGL and CUDA, but there's also still this careful state management because you're crossing API boundaries that weren't originally intended to be crossed. And the benefits with Vulkan SE come with the seamless sharing of data buffers like vertex data buffers or just general purpose data buffers, textures between the graphics and compute operations. Since it's all within one API, there's no crossing and changing ownership between these two different APIs, and there's no performance penalty associated with maintaining the OpenGL or OpenCL state for the application. And since it's all in one API, the application developer maintains total control of the state. And the other thing, which when you're comparing specifically against OpenCL and CUDA, is Vulkan SE is designed to be a certifiable API. OpenCL and CUDA currently do not have a path for certification. The OpenCL no one in Kronos is currently working towards doing a safety critical variant of OpenCL meant for avionics applications or other applications that require safety. And CUDA, NVIDIA, to my knowledge, has not done any work towards doing, for example, a DO178C certifiable version of CUDA. Now, the other thing I want to touch on, and I'm going to go over this very briefly since we are running close to the end of the time allotted for this webinar, is Openvx. And the VX portion of Openvx stands for Vision Accelerated. So you can kind of guess what the intent of this standard is. It's designed for accelerating computer vision applications. And it does this through providing a number of functions that are meant to be accelerated by devices like GPUs or other processing devices like FPGAs or neural network processing units. So it provides functionality to do hardware accelerated deep neural networks, as well as more classical computer vision operations like image filters, Gaussian filters, Sobel filters, edge detection, that kind of stuff. The other interesting thing for us is that, like Vulkan SE, there's a safety critical deployment feature set for Openvx that's really designed around exposing certain functionality to the user so that they can ensure that they're building an application that will be certifiable, that they're not using functionality that would be difficult to certify or would make certification more complicated. And something I want to kind of focus on here is the inclusion of neural networks in Openvx. And the reason that it is included in Openvx is because neural networks in general right now have proven to be the state of the art for doing object detection and object tracking. And the reason for this is that neural networks accelerate at finding non-obvious patterns in a data set. And this doesn't need to be like a 2D image data set. It could really be anything. It could be the point cloud of data. It could be very obscure data from a specific sensor. It could be audio data. It could be anything. And the reason neural networks accelerate at finding these non-obvious patterns is because they have these things called activation functions that introduce non-linearity into the operations that they're doing that basically allow it to find non-linear patterns within the data set. The other thing that's really useful for neural networks is that they have this discovery process that you do during training where you're providing sample data with expected results, and you do this thousands of times or even more than that, where you provide sample data, run it through the neural network, compare what the neural network produced with the expected results, and then adjust the weights, biases, and these other values associated internally in the network to make it produce the expected results. And you keep doing this and you're training the neural network, and you essentially discover an algorithm that's capable of doing the specific processing that you want to be done. Now, this does bring a lot of questions. I'm sure anyone who's heard of neural networks in this webinar is aware of the safety concerns that are around neural networks. And this is a very known area of research. There's a lot of focus that's being done on trying to solve this problem to make sure that we can classify a neural network as being safe, or classify the accuracy of the neural network so that we know the bounds, or how often it's going to produce problems, or in what cases it's going to produce problems. But this is not the only problem that exists when we're trying to deploy neural networks in safety critical applications. And it's especially when we're talking about deployment, there's the big issue of how can we ensure that the neural network executes in a known amount of time, that it uses a certain amount of resources. Because if you look at neural network frameworks today, like TensorFlow, PyTorch, Caffe, they rely on large software stacks, including Python, CUDA, OpenCL. Using this technology right now that is not certifiable, doesn't have guarantees about execution time, doesn't have guarantees about resource usage. And so even if you did manage to prove that the neural network was safe, you would never be able to deploy it in a safety critical system. And so Openvx kind of focuses on solving this problem, where we can ensure that the deployment of a neural network is deterministic. And once we've proven that the neural network is safe, or that we know the limitations of the neural network if we're using it in a lower safety requirement application like a DALC or DALI application, that we have guarantees about the execution time for a real-time system. And so this is what the Openvx is really focused on solving. Now, unfortunately, there's not a lot of time left in this webinar. If you're interested in the safety aspects of Openvx, whether with neural networks or the vision side of Openvx, ChorVI has published a neural network white paper on safety critical deployment of neural networks, focusing on how you can deploy them safely on GPUs. You can access that on our website. You can request a copy of these slides as well to access these links directly. Also, ChorVI did a previous presentation with Presages talking about more classical computer vision algorithms and how they can be accelerated by the GPU in a safe manner. So I'd encourage you, if you're very interested in this topic, to go check out the white paper or the previous presentation that we did. The last thing I'm going to focus on here is the certification. And so when we're talking about GPU compute, there's a lot of research being done on how certain algorithms can be accelerated using GPUs if they're a good fit for the way GPUs are architected. But a lot of this research is currently being done with library or tools like CUDA and OpenCL and others. And those of you who work in the avionics industry, I'm sure, are very familiar that safety is not something that can be just tacked on at the end. You know, we need to design from the ground up with safety as an intended function, and ensure that the way we're building our system is safe, so that we don't have to do radical changes later that can be, one, expensive, two, take a lot of time, and like three, fundamentally change our architecture. So it's important to ensure that safety is something that's being focused on from the beginning. So this concludes our webinar. I'm just going to do a little wrap up of the topics that we talked about today. So augmented vision systems in the cockpit can really benefit the user of applications. So when we're talking about advanced augmented vision systems, there's more information that we can provide to the pilot to make it easier for them to operate the aircraft. The usage of these systems needs to be understood so that we're not applying a higher cognitive burden for the pilot. We're actually making their jobs easier. But in order to enable these kinds of advanced augmented vision systems, we're going to require the combination of many sensors for redundancy and safety. Processing this amount of data from multiple sensors, correlating the data from multiple sensors, requires the use of high volume compute and hardware that's capable of high volume compute. And modern GPUs and standards around exposing the functionality of modern GPUs enables us to build high volume compute applications that are certifiable today. So I would like to say thank you for attending the webinar. If you have any questions, please ask them through the chat window. We're going to be going through the Q&A now. If you do want a copy of these slides, you can contact the email that is listed here and request a copy of the presentation. And now I'll hand it over back to Matt to start the Q&A.
Thank you very much for that, Lucas. And as Lucas mentioned, please feel free to submit questions through the chat window. I'm seeing a few coming through at the moment, so please feel free to kind of submit them as we're going along. As you can see, this is a kind of field that's kind of developing quite rapidly, and the kind of functionality in Core AVI and procedures are kind of doing work in this area. So we do encourage you after this webinar, if you are interested in this thing, please feel free to get in contact with us and look at the previous webinars we've done. I'm just looking through the questions here, and I'm going to try and field as many as we can at the moment. Let's just have a quick look. Sorry, there's quite a few here at the moment. I'm going to start off with, I think this one is possibly for you, Lucas. I've got a question here saying, I guess GPU can be seen as a massive multi-core processing unit, knowing the industry is struggling to certify a multi-core CPU system. Memory, how do you see the path for certification of a GPU-based compute system?
That's a very interesting question. So this is something that we are aware of. The GPU, yes, it can be seen as a massive multi-core processing unit. I don't think it's necessarily fair to compare it to CPUs because they work a little bit differently. Well, a little bit. They work very differently than CPUs themselves. They're not as general purpose as a CPU is. There's a lot of restrictions on how things can be parallelized around doing this computation. The other thing I kind of want to focus on is the types of applications that get accelerated by GPUs are the ones that are able to be processed in parallel easily. So this is when you don't have a lot of contention between cores. Like you have to do synchronization between the different parallel operations that are running, and you don't need to share data between these different parallel cores. And so in the type of applications that you would use a GPU for parallel compute on, the problems that are associated with doing massive multi-core certification are kind of removed. You're not worrying about the synchronization, because if synchronization was a problem for your specific application, it probably wouldn't be accelerated by the GPU well. If you do have an application where those things exist, then yes, the same concerns exist that are on the CPU. You have to make sure that the resource contention isn't going to dramatically affect the system. You need to make sure that that you're checking like the worst case execution time, that you're analyzing your specific use case to make sure that you know where there are resource contentions, like is it around a certain area, is there parts of the program that you need to do further analysis on. So I think that would be my answer, and I hope it better answers that question enough for whoever asked that.
Great, thanks, Lucas. I think there's one here probably for both of us here saying, are there special approaches for rotorcraft where low altitude map of the Earth visual is much more taxing in data volume, GPU loads, etc., versus fixed wing aircraft at high altitude? So I think that's a question about any special approaches for the low altitude.
So I guess I'll take that one first, and then you can add
Yeah.
what you think on top of that, Matt. So the interesting thing when we're talking about near Earth visualization, this is when high volume compute becomes more important. As Matt talked about in his presentation, when you're looking at things nearby, it's very important to have high accuracy, as 100-meter difference is way more important when you're close to the object than when you're 30,000 feet above the object. So this is where you start really having to be concerned about being able to process that much data efficiently. You need to have high resolution data that you have to process efficiently. The latency becomes much more important than it is at, for example, 30,000 feet. So I would say, yes, there are special approaches for rotorcraft, and that's when what we talked about in this presentation becomes extremely important.
Excellent. So I'll make a comment again. Actually, it's not just rotorcraft; it's anything that's the low altitude that it actually becomes a lot taxing. And I think that's where it gets interesting. The faster you move, or the lower the altitude, and combining the both together, I think rotorcraft are one of the worst case scenarios, which is why kind of compute starts working well. If we're looking at a high altitude approach and we're actually looking at large areas, it's an interesting difference between commercial airlines. If we're actually trying to use this type of system approaching a commercial airport, actually we have very large areas and wide spaces and a lot of tolerance, and typically you have reduced clutter as well. So it's not just the kind of high altitude, it's actually kind of just the amount of space. And I think those are the situations where we have already seen some SVS systems where you're seeing them on commercial coming into landing, and which is why it works, because there isn't a lot of stuff in the way, which means you haven't had to have the compute. I think this is where compute kind of comes into play, and obviously what you're looking for is trying to take the appropriate level, and it depends on the usage, I think, of why you're trying to do it. In the case of rotorcraft, is it we're trying to land on a small platform? Is it because we're in a brownout situation? Is it an unknown territory or something? If it's an area we know, we can be using databases to pre-process it to help. If it's a completely unknown, we're going to be having to do a lot of processing on the fly with the sensors on there. So I think there is a little bit of a, is it a known area or an unknown? If it's known, you can start using databases. If it's unknown and it's things, you're going to rely a lot more on the sensors. So hopefully that answers the question there. We've got quite a few more coming in. So I have a question here that says, how much crossover is there between aero and medical safety? Do you want to take that one, Lucas?
Yeah, I'm happy to take that one. So when we're talking about aero and medical, there is a lot of crossover, especially when we're looking at the safety side of things. Usually latency isn't as important with medical devices. Of course, it depends on the specific device that you're talking about, but it doesn't have the same real-time requirements when we're looking at an augmented vision system. There is important it is important to take account, like, can we process that data safely? Is it certifiable? I think that's where a lot of the concerns around medical devices come up. And when you're talking about devices like MRI machines, high volume compute is desirable there, because with an MRI machine, you're taking a large volumetric point cloud of the, someone's body that's very high resolution, and you'll need to process it fairly quickly if you want to have something fairly real time to display to the operator. So there is some overlap there. I think most of the overlap, though, is on the certification side, that proving that the system is safe, not so much on the latency.
Perfect. Got another one. I think you're getting the brunt of these, I'm afraid, Lucas. How long do you think until a certifiable application is implemented using Vulkan?
So we actually have customers who are working on certifiable applications right now. One public one I can talk about is the NASA X-59 project. So NASA is currently using Vulkan Safety Critical, a very early version of Vulkan Safety Critical, for an augmented vision system where they have a supersonic aircraft where they're trying to reduce the amount of glass that there is in the cockpit. And when I say glass, I don't mean like a glass display, I mean like the actual windows, so that there isn't as much concerns when you're flying as supersonic, and they're trying to visualize the underside of the aircraft in real time and show it to the operator. So that's something that's currently being worked on right now. That's going to be certified. So I don't think it'll be long before we start seeing the first applications that are running certified Vulkan in the world.
Okay. Another one, I think this is for both of us. What's considered to be acceptable latency in milliseconds for head tracking and scene updates for an AR display?
Hey, so I think Matt can probably talk to this more than I can,
Yeah.
but one thing I do want to say, I think it depends on what we're talking about. If you're
I was
looking
about
at
to say the same, Lucas, yeah.
yeah, if you're looking at a display, like it's a heads down display, the latency isn't as critical. I mean, it's still important. You don't want to have something that's misleading, but that's when, a 30 hertz, 60 hertz update rate where you're looking at, um, what is that, 20 milliseconds type,
Yeah, 15, 30 milliseconds.
50
Yeah.
seconds type delay, where it's not a big concern. But when you start going into heads up display, or even like, you know, a headset type application, the latency is much more important. That's when you start having to go, below 10 milliseconds. Like if you're not updating it quick enough, it can be not just distracting to the pilot, but it can also make the pilot sick.
Yeah. So I was going to actually answer the same way there. Depending on the application, there is some interesting ones. It depends on how fast you're moving your head and why you're doing the head tracking. Because actually there has been people using this or testing this system with human factors, and actually the update rate's pretty slow, but they're not using it for certain tasks, so actually the latency didn't matter. However, if I start using it as a pilot and I'm trying to scan around the sky and look at stuff, the kind of the classical head-up display rules start applying, because you don't do a head-up display typically less than 60 hertz. So you're looking at 15 milliseconds there for things to be updated on the screen, because you start getting disorientated because it is in your line of sight, and it's actually meant to correlate with the terrain and the actual scene around us. So I think you're kind of looking at a lower limit of around 15, which equates to around 60 hertz, or 16 milliseconds type of thing. And effectively what you're trying to do is improve. There is like a cutoff point anyway, because of the human kind of how fast it sees, reacts, and does things and processes stuff. So actually it's a kind of, if you go down to the 1 millisecond, it's kind of like there isn't very much point in that, because it actually doesn't help particularly in there. But you're looking to aim below the 15 really for that type of movement that's going to be correlated quickly to the scene. As I said, there are scenarios, and I've actually seen them, where again, it's interesting, at a high altitude and it's just trying to give me guidance, it doesn't matter that if I turn my head to the right and then I get information appear after a period of time after I've moved to the right, you have, yes, the data's been drawn, but it actually didn't appear. It's a kind of my classical example of a pop-up. It doesn't matter in that respect, because it doesn't matter that there was a latency for the information to appear, as long as it then keeps moving and correlating. So there is a different use case scenarios for where it is, but once we start getting into the high movement or low altitude and correlation with terrain and things like that, it becomes much more important on there. We have a few more coming in here as well. Where are we? There's a lot in here. Right. Embedded GPUs, though more performant than those available in the past, are nowhere near powerful enough as desktop devices. Have you a feel for what level of grunt, gigaflops, teraflops, would be required in an embedded GPU to provide acceptable responsive for real-time augmented reality?
Hey, that's a really good question. So, again, this is something that depends on what you're trying to do. If you're trying to do like the point cloud processing that we talked about in this presentation, you start getting the range where you want greater than 1 teraflop of processing. So for example, if we have a 60 hertz update rate, that gives you about 16 gigaflops per frame to process data. So that puts you in the gigabytes per second range of data that you can process per frame. And if you look at current embedded GPUs, like for example, the AMD 9171 or Intel's new integrated Tiger Lake GPUs, these are in that greater than 1 teraflop range in their embedded GPUs. So I'd say that we are in the domain where a lot of these applications are now approachable, like when we're talking about processing gigabytes per second of data. If you compare it to the lower end GPUs, of course, those ones are less than 500 gigaflops of processing power, and it starts to be very difficult to do things like processing high resolution point clouds. But you can still do other applications. So, for example, neural networks depending on how they're designed, don't require as much processing power as doing the high volume point cloud, especially if you're looking at image data. And so again, it depends on the application. But if we're talking about, cream of the crop, highest performance application, I think when you start looking at the modern GPUs like AMD Z9171 or Tiger Lake, or the Intel Tiger Lake Xe graphics, this is a reality now.
Okay, and following up, actually, there's a quite good one that's come straight in after that is IMX8 Quad was mentioned as a potential host for lower performance applications, simple graphics, no neural. Can lower performance hosts be used? Any sense of a minimal requirement?
So if you're just looking at simple graphics, no neural, I think you're not looking at an application that we talked about in this webinar. But of course, yeah, an IMX8 Quad Max could be used for simple graphics. It's more powerful than older GPUs that have historically been used in the avionics industry, like for example, the ATI M9 or the ATI M54. So it's a more powerful GPU than what was available on those systems, and those systems were used for simple graphics. So if you don't have any kind of high volume compute requirements and you just have simple graphics requirements, the IMX Quad Max is definitely a capable GPU to meet those requirements.
Cool. And another one here. This is actually definitely for you, Lucas. This is Openvx. Can work with convolution neural networks? Can it work with a convolution neural network? I think that's
Yes.
the
Yeah.
okay. There, I think that was a quick answer.
Yeah. So Openvx, it works with convolutional neural networks. Openvx isn't really tied around specific types of neural networks. It has support for convolutional layers in a neural network, and many of the common activation functions associated with it. It would be kind of silly if Openvx didn't support convolutional neural networks, since those are,
Yeah.
if you look at the research done currently right now, those are the best performing types of neural networks for object detection and object tracking type applications.
Perfect. And I'm just going through, as I said, thank you for all your questions. We do appreciate these as well as they're coming in. I've got one here just as a general question, actually. Does the application of this technology apply equally to commercial and military? What about ground and airborne applications? So I don't know if you've got any comments on that, Lucas. I've got a few to comment.
Yeah, so I think this technology is applicable in both domains, defense and commercial. When you're looking at commercial helicopters, a lot of this stuff is very useful. When you're looking at commercial aircraft, having night vision systems, especially when you're landing at night, are extremely useful and can aid the pilot and reduce crashes associated with low visibility at nighttime. And then there's other, I would say, more obscure applications where, for example, if the view in the cockpit was obstructed for any way, for example, like say if there's a fire in the cockpit with smoke, having an augmented vision system like this could be very valuable to make sure that the aircraft can still land safely in the event where there's, some would say catastrophic failure in the cockpit. In military, of course, there's a lot of applications for this. I don't know if I can go into all of them in this presentation, but degraded visual environments is a big application for military. Augmented vision systems are very valuable for degraded visual environments. I think I'll hand it off to you, Matt, to answer your side of this.
Yeah, so I think it's a good question because yeah, this sort of technology applies both to commercial and military. There's been a lot of use of kind of vision systems in military over the years, but obviously there's a lot of specialist purpose behind that, and people can see those things. But actually in the commercial world, it becomes more valuable as this technology becomes more widely available with safety consideration. So if we were looking at commercial airlines, we're already seeing SVS appear. But now we're adding in the capabilities of other tasking or other types of domains. And actually, helicopters are a perfect example in the commercial world where these type of systems can help a lot, because actually helicopters are a little bit more like military fast jets, that they deal with low altitude, high movement, and they live in a very cluttered environment, and they have to deal with some very inhospitable environment. So be it fog, obviously we have the military uses for brownout in kind of desert places. I wouldn't expect commercial to be trying to land in unhospitable, but you actually get the weather conditions where you're trying to land, you get oil fields and oil rigs trying to land in those type of environments. You're landing in other areas where you don't have the space. You have a cluttered airspace, you have restrictions, flying within the city, that type of thing. And obviously you've got your newer types of vehicles as well, where more like the helicopters. And if we look at the kind of ground side, you've got the similar sort of situation, these type of things where there is a valuable use. If you look at ground military vehicles, if you've got obscured views because of dirt or kind of, again, weather conditions or mud, kind of those things sound strange, but when you're driving a vehicle on off-road, you get a lot of that type of setup in there. And you have similar sorts of problems you're trying to deal with. You can't see what you're driving over. You don't know where you're going. You can't see because of kind of critical conditions. So I think this technology is actually got a lot of applicability in the commercial airspace and also in the kind of ground environment as well. So I'm just going down, just looking at further questions on here. I think there's a question, does procedures help facilitate some of this development? I think the answer to that is yes. We've got quite a few tools actually on the sensor simulations side to actually help you model this and predict what's going to happen, and they're physics based. And then obviously as procedures, we've had a long background working in kind of graphics and real-time rendering. So if you're interested, please feel free to contact us and we can talk about tools on there. And I'm just looking through, as I said, quite a lot of questions trying to go through, and I'm just keeping an eye on the time. I think we can probably do one or two more questions. I think there's one here. Can Vulkan Compute do everything OpenCL and CUDA can do? So I'll hand that over to you, Lucas.
Okay, thank you very much, Matt. So that's a good question. When you're talking about general purpose compute, Vulkan is capable of doing everything that OpenCL and CUDA expose, more so with OpenCL. CUDA is a little interesting because it's more than just a framework to write compute shaders for GPUs. There's a lot of the library of functions that are exposed in CUDA. And so Vulkan is, of course, capable of implementing all of those functions, but it's not provided with the API by itself. If you're interested in having more of those types of library functions, that's where we at CoreVI see Openvx, and we have another product called Compute Core fitting in to provide these types of library functions that make it easier to build compute applications. But just from a general purpose, like functionality perspective, yeah, Vulkan is capable of doing the same type of compute operations that OpenCL and CUDA can do.
Perfect. So I'd like to thank everybody here. I know there's a couple of more questions, but what we're going to do is wrap this up. If you do have any more comments, questions, feedback, please feel free to contact us. If you want a copy of the presentation, you can reach out to the EG Marketing at Procedures. We'd appreciate, obviously, when you leave this webinar, if you could fill in the survey, give some feedback to Lucas and myself on the topics, any way we can improve on this type of information. And if you are interested in looking or are working in this area, please feel free to reach out to kind of Procedures and CoreVI. We're more than happy to kind of go into deeper discussions with people on these topics. So thank you very much for attending, and we appreciate your time. Goodbye.